Start recording. Alright. Okay. Good morning, everyone. Hope you all had a good weekend. So, does anyone have any quick questions on the related rates homework? No? Okay. Okay, so, just a couple of quick announcements. Quiz, I believe it's 6, I think we're on. Opens up on Wednesday, and you have until Thursday to complete that quiz. And I think it said it covers lessons 15 and 16, I believe. Yeah, that sounds about right. And then there's exam 2, which opens up on Saturday, and we're going to have a review on Friday for that. So make sure to come with any questions you may have. And what I'm also going to have happen a little bit later today is I'm going to have the extra credit 3 opportunity is going to open up this week. So what's going to happen is I'm going to send you guys a packet of review problems for you to look at for exam 2. So what I'm going to do is I'm going to say, okay, do usually one problem from each set of lesson or set of lessons, depending on what the page covers. So I'll send more details about that in an email later today, but just keep a lookout for that. Okay. So other than that, any questions on anything? All right. So let's move on to a brand new topic, which I promise is much easier than anything from last week. So that's going to be relative extrema and critical numbers. So here's a couple of quick definitions. So if f of c is greater than or equal to f of x for all x in some open interval I containing c, then f of c is what's known as a relative maximum. Okay. So I'll give you guys a picture of that in a minute, but for the next line, it's going to be similar, except we have f of c is less than or equal to f of x. And then for all x in some open interval I containing c, then f of c is going to be what's known as a relative minimum. So if f of c is less than or equal to f of x for all x in some open interval I containing c, then f of c is a relative minimum. So what you may notice is that this definition here doesn't really use the idea of a derivative. And you'll see why in a minute, but for now just keep that in mind. So no derivatives needed here. Okay. Okay. So let's give us a picture to see what I mean by this. So here's a picture of some function f of x. Okay. So let me just make that a little bit higher. There we go. Okay. So to give you an example of what I mean by relative max and min, let's go ahead and take a look at this point here and this point here. So here's what we notice. So let's take a look at f of c1 and f of c2. So here's what you notice. So if we take a look at f of c1, then what you notice is that, well, it's clearly not the highest value of the graph, but what we notice is that if we take just some open interval I containing C, so C1 goes here, then what we notice is that, well, like we said, f of C1 is clearly not the highest point on the graph, but it's definitely the highest point around the set of points here. So, like we said here, all we need is just some open interval. We don't need to focus on every single open interval, just one. If we need to pick just one, then that's enough for us. Because what you notice is that, like I said, not the highest function value period, but it's the highest function value in some open interval around the point. So in this case, f of C1 is a relative maximum. Or you can call this a quote-unquote mountaintop. Okay. And then in a similar fashion, well, f of C2 is clearly not the lowest point on the graph, but f of C2 is the lowest point for some interval around that point. So if we restrict to some interval around C2, it is definitely that lowest value. So in this case, f of C2 is a relative minimum. So valley / dip. Okay. So in this case, that gives us the idea of what a relative max and relative min is. It's not the highest value at all, or the lowest value at all, but it is if we restrict to some interval around the point. Alright? Okay, so that's the idea behind relative minimum and relative maximum, but it's going to get a little tedious if I keep saying relative minimum and relative maximum 500 times, so let's give this pair of definitions a nice name. Let's call them relative extrema. Okay? So either a relative minimum or relative maximum. But here's the catch. But one thing you need to make sure of is that f of x has to be continuous around these extrema. F of x must be continuous. Okay? So what I mean by that is that you can't have any holes, no jumps, no vertical asymptotes, those things we talked about earlier in the semester. So i.e., no holes, jumps, or vertical asymptotes. Right? So that's the first part of today's lesson. The other part is this idea of critical numbers, or what I'm going to call critical points. So more generally, we have this notion of critical points, or I'm going to abbreviate them as CPs. So critical points are values of x, and one important thing to keep in mind here is that they have to be in the domain. In domain of f of x, where f prime of x equals 0, or f prime of x does not exist. Okay? So let's take a look at what each of these mean. So we've kind of already seen what f prime of x equals 0 looks like already. We've kind of seen this idea before. So let's briefly go over that real quick. Then if f prime of x equals 0, then you're going to get something that has a horizontal tangent line with slope is equal to 0. So essentially, you're going to get something that looks like this. So critical point means you either have horizontal tangent line with a relative minimum, or maximum, sorry. A horizontal tangent line with a relative minimum, or you have a horizontal tangent line but you don't have a relative extrema at that point. So f prime equals 0, but neither min nor max. Okay? So because of that, what that says is that, all right, well, if we have a relative extrema, then based off these two graphs here, it must be a critical point. But critical points don't always have to be relative extrema based off this third picture. So relative extrema are critical points, but not other way around. Okay? Okay. So yeah, there's a lot of setup here, but that's kind of, if we're doing a new topic, that's kind of a bit inevitable, unfortunately. So any questions so far? Okay. So like I said, we kind of already seen what this f prime of x equals 0 situation looks like already. But what does f prime does not exist look like? Well, that's where our next page is going to come into play. So what we're going to do is we're going to consider this function denoted by the absolute value of x that says, okay, so if we have some positive value or non-negative value, then we just get the original value back. So in this case, if we have, say, absolute value of 3, then it just spits out 3. But if we have something that's negative, well, we have to take the negative of that in order to transform this into something positive. So in this case, we have negative of negative 3, so just 3. So basically, if there's a negative, it gets rid of it. But if there isn't, then just leave it as it is. So graphically, what this looks like is that you're going to essentially end up with some v-shaped function. That's what you ultimately end up with here. So that's what f of x looks like in this case. So what you'll notice is that, well, even though there's you can pretty quickly see that there's a relative minimum at x equals 0, but what do we also notice? So if you take a bit closer of a look, you'll notice that there's more of a sharp turn at x equals 0 as well. So sharp turn at x equals 0. Okay? So let's take a look and analyze that right quick. So if we have that, then let's go ahead and take a look at the differentiability of this. So if x is greater than 0, well, as we already established, well, that tells us that f of x has to be equal to just x. So if we take the derivative of that, we say, all right, well, a quick application of power rule should pretty quickly tell us that in the case that x is greater than 0, then its derivative should then just be 1, right? Okay? And then if we do a similar thing with x less than 0, well, we have f of x is equal to negative x. So then a quick application of power rule should then tell us that f prime of x is then equal to what? Negative 1, right? Okay, so nothing too crazy there. So that says, all right, well, so if x is not equal to 0, then we're fine. The derivative is well defined, and there's nothing we need to worry about here. So now, let's see what happens at x equals 0. What goes wrong? So recall, if you want to figure out the derivative, remember one way to do it is go by the very first definition we saw in class. Namely, we have to use the limit definition. So if you recall, that says the limit as h goes to 0 of f of h minus f of 0 all over h. Now in this case, we did have the x plus h and x here, but in this case, if x is equal to 0, then this just simplifies to this here. Okay? So what you'll notice is that, well, f of h, well, that's just h, or absolute value of h, minus f of 0, which is, well, 0. So ultimately, we just have absolute value of h divided by h. So here's the kicker with this. This corresponds to the two-sided limit, right? So if you want to figure out the two-sided limit, remember, we had to break this up into the corresponding one-sided limits to see what ends up happening from this. So in this case, if we take, say, the limit as h approaches 0 from the right, and h approaches 0 from the left, that says, okay, so we have the limit as h goes to 0 from the right, and limit as h approaches 0 from the left. So in this case, if we approach 0 from the right, then that says, okay, so that means that this fraction here simplifies down to what? So absolute value of h, if h is, we're approaching 0 from the right, that means that absolute value of h becomes what? So approaching 0 from the right, that means we have to be slightly greater than 0, right? So what does absolute value of h simplify to here? There a number? Well, in this case, it's just, so if h is greater than 0, right, that just means it's h, right? So in this case, you just have h over h because of the fact that we're letting h get really, really close to 0 while also being greater than 0. So because of that, we have to use h here. So you can tell pretty quickly this just simplifies to 1 because, well, this fraction becomes 1 and that's that. And similarly, because we have the limit as h approaches 0 from the left, well, absolute value of h then just becomes negative h divided by h. But, oh, wait a minute, this simplifies to negative 1. So, remember, so if that tells you that these one-sided limits don't agree with each other, then that should tell you that the corresponding derivative, or the limit, should then be what? If the one-sided limits don't agree with each other, we had, well, yeah, it does not exist. Okay? So let's take a look at the graph of f prime from that. So we say, all right, so we already established if x is greater than 0, the derivative is just 1, so we just have that this is just 1. And if x is less than 0, we have f prime is negative 1. So as a result, this is what the graph of f prime of x is going to look like. And because f prime of 0 does not exist, we have to incorporate these not filled in holes here. Okay? So, as a result, what we can say is that f prime of x does not exist. Graphically, yields quote-unquote sharp turns like kinks. Looks something like this. Cusps. And corners. Okay. Otherwise, prime of x is equal to 0. Okay. So basically, if we have that's a sharp turn, then you're going to have something like this, or one of these three. So the derivative does not exist. But otherwise, the derivative has to be 0 at that point. Okay? So, any questions on any of that? So we'll give you guys a second to write that down because we're going to need the entirety of page 3 for the next example. Does anyone still need page 2 stuff? Okay. All right. Example 1. So we are tasked with finding and classifying the critical points of f of x, whose graph is given below. So here's our graph. So basically the point is we have this little chart here we got to fill out. So we have critical points here, so that says, all right, if we have that this is our graph, then we should figure out where the derivative is either 0 or does not exist. So let's go ahead and go down the line and see where we could have that happen. So I'll do one of them for you guys just to give you an idea of what's happening. So if we go down the line, well, what we notice here is that, oh, wait a minute, looks like we have one sharp turn already. So that will correspond to the critical point at -10 here. And because we already established that this would be a sharp turn, then this would mean that the derivative does not exist here. And then because, well, if we take some open interval around -10, well, what we notice is that it may not be the lowest point at all, but it is the lowest point if we restrict it to some interval around -10. So as a result, this will be a relative minimum at, well, they already give us -10 comma -7. Okay? So that will be one example just to give you guys an idea of what's happening here. Okay? So let's go down the line and see what other points we get. So at this point, this table should indicate that should be at most 5 more critical points. So let's go ahead and look at the graph and see what else we can find. So what will be the next x value at which you have a critical point?
-2.
Yep, -2. And does the derivative equal 0 or not exist?
0.
Yeah, 0. Why?
Because it's continuous.
Well, it's continuous, but more importantly, it's no sharp turn, right? Right. Okay. And would this be a relative minimum or maximum?
Maximum.
Good. Okay. Maximum at, well, they already tell you the point, so -2 comma 4. Okay. So that's our next point. So then someone else, what will be the next point after that?
0.
Be 0, good. And would the derivative equal 0 or not exist?
Not exist.
Not exist, good. And relative min, max, or neither?
Or neither.
Neither, right? Because in this case, if we take any open interval around 0, what we notice is that, well, it's not the highest point, nor is it the lowest point. So it can't be either. So neither at 0 comma 2. Okay, so keep going down the line. So what's the next one?
5.
5?
0.
0? Min, good. So 5 comma -6. All right, then someone else, what's the next point? 8?
And then 0.
Okay.
And then neither.
Neither. Good. That's 8, comma 2. And then the last one.
11
Yep, 11.
does not exist,
Does not exist.
and max.
Max. Good. Okay. And then at 11, comma 3. All right. And that's example 1, because we've exhausted all the points at which we have a critical point. So that's example 1. Okay. Any questions on any of that? All right. So let's move on to example 2. So example 1, we had a graph of f of x. So now 2, we're going to be given actual algebraic expressions for f of x. Okay. So anyone still need? Okay, looks like we're good. All right. So now, moving on to example 2. Find the critical points of f of x equals x cubed plus 4x squared plus 5x. So if you recall in the definition of critical points, one thing we had to make sure of is that we had to make sure the values of x have to be inside the domain. So let's take a look at the domain of this real quick before we really start with this properly. So since it's a polynomial, this should pretty quickly tell you that the domain of f of x is just what? Yeah, so the entire real line. So negative infinity to positive infinity. Well, so at first you might think that just seems silly, like, okay, well, it's clearly the entire real line, so why do we need to check this? Well, it does seem silly now for the next 2 examples, but with the third example we're going to see in a bit, that actually will come into play. So, just something to keep in mind. So, as per the definition of critical point, we have to check, well, we have to check where the derivative is equal to 0 or does not exist. So, let's check the derivative. Well, quick application of power rule should tell you that the derivative is equal to what? What function? Go ahead.
3x squared plus 8x plus 5.
Yep, plus 5. Okay, so that's the derivative. Nothing too crazy with that. So the nice thing is that, again, this is just another polynomial, right? So this is defined everywhere. Defined everywhere. Okay, so the good news is that there's no way for this derivative here to be non-existent. So all we have to do here is just check, well, when is this equal to 0? So, in this case, how would we do that here?
Could we factor it?
We could, but how would you factor it? Yeah, it's not super easy to see, is it? So in this case, a good last resort will be the quadratic formula, right? So let's go ahead and apply that. So if you recall, that says, okay, well, if you wish to apply the quadratic formula, well, does anyone remember if we plug in our coefficients, what that says? What our good old quadratic formula gives us? Okay. All right, so sounds like we need a bit of a review then, which is, it's okay. Just wanted to see if you guys remember. So, let's see if I remember the song for this. X equals negative 8 plus or minus square root of 8 squared minus 4 times 3 times 5 all over 2 times 3. So, basically, the song was, if you remember, it's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Did anyone remember use that song when they were? Okay, thank you. Glad I'm not the only person that's like using the song. Okay. Did anyone else learn it? Because Okay. Okay. All right. Good. Good. Not good. All right. All right. So you apply the quadratic formula song to remember the quadratic formula, and then you plug in the corresponding coefficients to get this thing. All right. So we have -8 plus or minus the square root of, well, 64 minus all this, 4 times 3 times 5. So you can either do the math in your head or plug this into a calculator to get that this simplifies to what? Yeah, just 4, right? Because 4 times 3 times 5, that's 60. Because 4 times 3 is 12. Multiply that by 5 is 60, so that's that. And 8 squared is 64. And then downstairs we have 2 times 3 is 6. So, well, -8 plus or minus root 4, that's -8 plus or minus 2 over 6. Okay, and then so that should tell you that, well, if as a result your two solutions to this quadratic should then be what?
-1 or negative, I guess, and negative 5.
Exactly. Because in this case you have, well, -8 minus 2 over 6, and then -8 plus 2 over 6. Okay? So we have -10 over 6, which is -5/3. So that's one of them. And the other one is -6 over 6, which is just 1. Okay? So in this case, your two critical points that you need are -1 and -5/3. All right? So that's example 2A. So any questions on that? All right. So moving on to part B from this, we have, all right, f of x is now equal to x cubed times e to the x. So as I already sort of hinted at a bit earlier in the last sub-example, the domain of this is also the entire real line. Okay. But now, if we want to take the derivative of this, well, what's going to happen if we take the derivative of this? Go ahead.
So that would be 3x squared, and then with the 3x to the same.
Yep. And e to the x, and then plus. X cubed e to the x, right? Remember, you have one function of x times another function of x, right? So in this case, you're going to need to use product rule to get the derivative here. Okay. So that takes care of that. And then the nice thing with this example is that, well, what would the domain of this thing be? Or I guess, is there any point at which this would not be defined? No. So we're good, right? So this is defined everywhere. Defined everywhere. So like we said, like we had in the last example, all we need to do is check where this is equal to 0. So with a problem like this, we say, all right, if we want to figure out where all values of x where we get 0 here, then we should probably start by factoring anything that could make this a bit easier to simplify. So if we do that, we say, all right, what can we factor out of both terms to make this a bit easier on us?
X squared e to the x.
Yep, x squared e to the x. So we have x squared e to the x. So if we factor that out, we end up with, well, 3 on the first term, and then plus x on the second term. Equals 0. So then that should pretty quickly tell you that the critical points that we need here are what? Yep, just 0, -3, right? Because x equals 0 from this, and then x equals -3 from this factor here. So that's part B. So any questions on that? Okay. So moving on. Okay. So moving on to part C from this. So before we move on to part C properly by finding the derivative, there's a bit of a catch with this. So let's start by finding the domain of this thing. So we have x to the fourth minus 4 over x squared. So what would the domain of this thing be?
Is it all real except for 0?
Yep. So all real values except for 0. So x cannot equal 0 here. Or if you wish to use interval notation, we have negative infinity to 0, union 0 to infinity. Okay? So just something to keep in mind for this example here. So in this case, now let's go ahead and take the derivative of this. So what you notice is that, well, even though we do have a quotient here, and hence can use quotient rule, technically speaking, would that be the most optimal way to take the derivative of this? No, it's not. So what would be a better way to do it? Or, I guess, more optimal way to do it? So here's a hint. So both of these terms here have a common denominator of x squared down here, right? So we could break this off as x to the fourth over x squared minus 4 over x squared, right? So in this case, we say, all right, so how does this simplify? So x to the fourth over x squared is just x squared. And then the second term becomes 4 times x to the what power? Negative 2, right? So now let's go ahead and take the derivative of this. So if we do that, we get that the derivative becomes what? Let's give someone else a chance. Go ahead.
2x plus 8x to the negative third.
Yep, 8x to the negative third. Or, if you prefer, 2x plus 8 over x cubed. So, now here's a catch with this. So, like we said, we have to make sure to check where are there any values of x at which this is undefined / does not exist. So if we take a look at this, we say, all right, so like we had before, well, we can't really divide by 0. So defined at x not equal to 0. But, oh, wait a minute. Remember, the definition of a critical point said we have to focus on the values of x in the domain of the original function, right? So as a result, but x equals 0 is not in domain of f of x. So we can just completely disregard this here. So disregard. Okay? So because of that, we don't care about x equals 0 as a critical point in this problem because it's not in the domain. So that automatically disqualifies it as a critical point here. Okay. So at this point, the only thing we can do is just, well, take the derivative and set it equal to 0 as we've been doing. So 2x plus 8 over x cubed equals 0. So let's go ahead and solve for x from this. So if we do that, what would be the next step from this? So what would you want to do? What would your next step be? So in this case, one thing we could do is say, all right, let's take this 8 over x cubed and subtract it over to the other side. So we have a negative 8 over x cubed. Then the next thing we can do is say, all right, well, we have an x cubed in the denominator here. So we could multiply that by multiply to both sides to get 2x to the fourth equals negative 8. And then divide 2 to both sides to get x to the fourth equals negative 4. But, oh wait a minute, are there any real roots of this thing? This x to the fourth equals negative 4. There aren't, are there? So, no real roots of this thing. Because of the fact that this is an even power. Even power. So because of that, there are just no critical points here. No critical points. So, yeah, that's all we can say. Just no critical points. All right. Okay, so any questions on part C? All right. Okay, so the last thing we're going to do is look at part D. So we have f of x equals 2 times cosine of 2x plus 2x. So the thing is that, well, even though this is technically defined on the entire real line, the catch is that we have to restrict it to this interval 0, pi. So in this case, our domain in this case is just 0, pi in this case, because the problem explicitly says restrict to that domain. Okay? So, that's all we can really say on that. So let's go ahead and take the derivative as we normally do. So f prime of x would then equal what? Go ahead.
Negative 2 sine of 2x plus 2.
Careful. Remember, there's a 2x inside a cosine.
Number 4.
Right, so remember,
Yeah.
yeah, because remember, chain rule is still a thing. Chain rule. Okay, so let me do this. So I'll say negative 2 times cosine of 2x. And then because of chain rule, you have to multiply this by the 2 inside. You have to multiply this by the derivative of 2x. And then add 2 to this. So ultimately you have negative 4 times cosine of 2x. Oh, sorry, sine. Whoops. My bad. That's on me. So negative 2 times sine, and then sine here. Sorry about that. So, okay. So the good news is that, again, this is still defined everywhere, so all we need to do is just check when this is equal to 0. So if we solve for sine of 2x here, what we notice is that, well, you should pretty quickly see that sine of 2x just becomes 1/2. So what we need to do here is say, all right, we need to figure out all values of x for which this equation holds. So what we're going to do first is we're going to say this. So to solve for x, first, let's u equal 2x and solve sine of u equals 1/2. Okay? Just to break things up and make things a bit easier to digest here. Okay? So as a result of this, we say, all right, if we just focus on just this part here, we have that if sine of u equals 1/2, then U equals what? So now at this point, let's just focus on the entire unit circle, not focusing on, any particular quadrant here. Just say, what can U equal here? So you're talking back to our unit circle.
Is it pi over 6 and 5 pi over 6?
Yep, pi over 6 and 5 pi over 6, right? Okay. So those are two such values, but what I'm going to do is I'm going to go a bit further just for the sake of making sure we have some nice basis here. And I'm actually going to say, all right, I'm going to take these two and then I'm going to add 2 pi to them. Because if pi over 6 and 5 pi over 6 are solutions to this, that means that any integer multiple of 2 pi added to these are also solutions to this, right? So what I mean by that is that if I add 2 pi to these, that means that these should also satisfy this equation here. So we have 13 pi over 6 and 17 pi over 6. Because these are pi over 6 plus 2 pi and 5 pi over 6 plus 2 pi. Okay? So these are, remember, these are still equal to 2x here. So if you want to ultimately solve for x, well, just divide by 2 on those solutions to get what you want. So x can equal, well, if we divide 2 to each of these, we should get pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. Okay? So as a result, that says, okay, so if you want to focus on the domain 0, pi, which of these 4 would be in that domain?
The first two.
Yeah, just the first 2, right? So that's your answer. That means that the desired critical points are just these 2. Okay? So that's it. That's all I had for today. So, you guys have any other questions on any of that? All right. Well, then I will see you guys on Wednesday, or I will also have Zoom office hours tonight. But yeah, other than that, there's that, and then also make sure to keep an eye out for a challenge problem packet on my webpage for extra credit opportunity 3. So I will send an email later today about it.